This video is for Chemistry in the Earth System, Unit 1.1, Heat. Today's essential question is, how does thermal energy transfer, or heat, cause substances to change state? Hello, baby birds. Before we crunch numbers, let's frame our journey. Thermal energy, which is the energy tied up in the motion and arrangement of particles, rules every cup of coffee that cools on your desk or every geyser that erupts in Yellowstone National Park. When this energy moves in or out of matter, one of two things happens. The particles speed up, meaning the temperature rises, or the particles reorganize, which means the substance changes state. In this video, we'll untangle those two effects, trace them through a heating curve graph, and see why huge hidden energy bills called latent heats make steam engines, refrigerators, and geysers possible. By the end of the video, you'll be able to explain, calculate, and predict phase changes in any everyday or extreme scenario. Thermal energy is the total kinetic energy and potential energy of every atom or molecule within a substance. Imagine stacking pennies. One penny is temperature. The whole stack is thermal energy. Because it sums across all particles, a bathtub of 40 degrees Celsius water stores far more thermal energy than a thimble of 100 degrees Celsius water. Temperature, by contrast, is an average. It tells us how fast each individual particle vibrates or translates on average. Add the same 10,000 joules to a teacup and a bathtub, you'll see that the teacup's temperature spikes. The bathtub barely budges because those joules spread across millions more particles. Keeping thermal energy and temperature straight is crucial for the rest of this video, especially when we meet plateaus on the heating curve. Matter shows up in four familiar outfits. Solid. Particles are locked in place, vibrating but not translating, meaning they have a fixed shape and a fixed volume. In a liquid, particles slide past one another, meaning they have a fixed volume, but they shape to the container. Gas. Gas particles dart freely and occupy any space, meaning they have variable volume and variable shape. Plasma. Electrons stripped away from their nuclei, a soup of charged particles with extremely high kinetic energy. The differences between these boil down to two variables: the kinetic energy of the particles and the strength of the forces pulling them together. Raise kinetic energy, or weaken attractions, and you move rightward on this list. Do the opposite, and you'll move left. As Yellowstone water ascends, it journeys through all four: liquid when it's deep underground, superheated liquid in the conduit, explosive steam right at the vent, and then an ionized plasma glow visible at night when lightning strikes that same plume. Suppose you turn on a burner beneath a beaker of ice. At first, every joule you add shows up as faster vibration. Temperature rises steadily. This is a sensible heat phase, meaning energy you can sense on a thermometer. But as soon as the ice reaches 0 degrees Celsius, something dramatic happens. Even though the burner keeps pumping energy in, the thermometer stalls. You're now paying the entrance fee to the change of state. Energy is busy loosening hydrogen bonds so that the rigid lattice collapses into a flowing liquid. Only after every last crystal is gone will the temperature climb again. Exactly the same story repeats at the boiling point. So, thermal energy has a dual personality. It can raise temperature or bankroll a phase change, but neither both at once. A phase change is a reorganization of particles without a change in their average speed. So during melting or boiling, added energy strengthens the amplitude of the vibrations only enough to break intermolecular attractions, but not to accelerate the particles any further. That's why the temperature graph flattens, even while a hot plate hums beneath the beaker. Electrostatic potential energy will grow. Kinetic energy sits on pause. In reverse, meaning freezing or condensing, the same quantity of energy is released as attractions reform. But again, the thermometer stands still until the transition finishes. Phase change temperatures are fingerprints. They act as fingerprints for the substance's identity and its surroundings. At sea level, water melts at 0 degrees Celsius and boils at 100 degrees Celsius. Silver, which is bound by far stronger metallic bonds, doesn't melt until about 962 degrees Celsius and boils near 2212 degrees Celsius. Pressure tweaks these numbers, however. So if we climb a mountain and air pressure drops, then water will boil at around 93 degrees Celsius. For example, in Yellowstone. Descend into a pressure cooker and water won't boil until about 120 degrees Celsius. That dance between pressure and temperature explains why deep conduit water in Old Faithful, a famous geyser from Yellowstone, can sit quietly at 96 degrees Celsius, which is far above its local boiling point, until the eruption pathway opens and the pressure collapses. A latent heat is the hidden energy toll for a phase change at a constant temperature. So here's a term, latent heat of fusion, represented by L sub F. For water, this value would be 334 kilojoules per kilogram. This is the amount of energy required to melt ice, 334 kilojoules per kilogram of ice. We also have latent heat of vaporization, represented by capital L sub V. Also for water, it's going to be 2,260 kilojoules per kilogram in order to turn liquid into steam. What vaporization fee is more than 6 times the fusion fee? Why is it so steep? Because in boiling, particles must fully break free of attractions to neighboring molecules, not just loosen them. This huge value is why steam carries so much energy for industrial turbines, for example. And that's why a geyser's roar is powerful and powered by an explosive expansion the instant that latent energy crashes out. Nature balances these energy books perfectly. The energy you pay going up the ladder during a phase change is exactly refunded as you come down. Add 334 kilojoules to a kilogram of ice, and you get water. Remove 334 kilojoules, and it refreezes. Dump 2,260 kilojoules into a kilogram of boiling water, and it becomes steam. Pull that exact same 2,260 kilojoules back out, and the steam condenses. This symmetry underpins every refrigeration cycle and every thundercloud downpour. So let's walk this curve from left to right. So we have solid warming. We have in the negatives, let's start around negative 20 degrees Celsius rather, all the way up to 0 degrees Celsius. Here we see energy rising, right? The energy is actually raising the temperature because it's all kinetic movement, increasing the acceleration of the particles. Then, once we get to 0 degrees Celsius, we reach a melting plateau. This is where energy is not used to increase the movement of the particles, but it melts the ice. This is why the temperature flatlines. We move up again, we get liquid warming. This is between 0 degrees Celsius and 100 degrees Celsius. Again, energy translates directly into higher kinetic energy, meaning more energy of movement. But then at 100 degrees Celsius, we reach a boiling plateau. Energy bankrolls here into vaporization, and temperature stalls. And then after that, we get steam warming. Above 100 degrees Celsius, as long as the pressure allows, the slope's steepness reflects specific heat. Liquid water's specific heat is roughly double that of ice, so its slope is gentler. Plateaus reveal where latent heats lurk. A heating curve is your diagnostic tool. Any flat region screams phase change in progress. You can count the joules required for each plateau, and you can tally latent heats experimentally. Engineers, for example, size HVAC units. Chemists design distillations, and geologists model geysers with these same plots. In Old Faithful, that famous geyser from Yellowstone, temperature climbs slowly at depth, plateaus during a hidden flash boil, and then plummets once steam vents, mirroring our textbook curve on a grand scale. Let's talk about superheating and supercooling. So let's start with superheating. A liquid that is superheated is pushed above its boiling point because either high external pressure or a lack of nucleation sites blocks bubble formation. Geyser conduit water, sitting at 96 degrees Celsius, which is several degrees above the local 93 degrees Celsius boiling point, is superheated. A tiny pressure drop or an escaping bubble triggers a chain reaction and then a violent phase change. On the other hand, supercooling. A liquid that is supercooled is chilled below its freezing point, but stays liquid for the opposite reason. No crystal seeds. Now, if you jostle a supercooled water bottle, it will freeze before your very eyes. Now, both states, being superheated or supercooled, are unstable, and when conditions shift, the delayed phase change releases or absorbs energy in an instant. Phase changes aren't just academic. They also drive technology. Refrigerators or AC units. For example, in one of these units, a refrigerant repeatedly evaporates, meaning it absorbs latent heat inside the fridge and then condenses, which dumps that heat outdoors. We also have common hand warmers. A supersaturated sodium acetate crystallizes when you click a metal disc, releasing latent heat fusion to warm your cold fingers. Also, geothermal power. Underground water flashes to steam, spins a turbine, condenses, and then recycles. Earth does the heating. Gravity provides the return flow. In each of these cases, engineers exploit the giant reservoir of energy hidden in latent heats. Now, we can stack these numbers side by side, and we see the transition from ice to water takes about 334 kilojoules per kilogram of water. But the transition from liquid water to steam takes much more energy, 2,260 kilojoules per kilogram of water. That 7-to-1 ratio explains why steam engines changed the world and why steam burns are so severe. 1 kilogram of steam at 100 degrees Celsius carries enough latent heat to melt almost 7 kilograms of ice without its temperature dropping by even a single degree. So let's recap the lesson. Thermal energy can manifest as rising temperature or hidden latent heat, but both never at once. Phase change temperatures are substance specific and pressure dependent. Latent heats, for example, 334 kilojoules per kilogram for melting ice and 2,260 kilojoules per kilogram for vaporizing water, are enormous energy reservoirs. Energy conservation in phase changes is exact. Pay in going up, cash out coming down. Applied wisely, these principles cool groceries, heat homes, spin turbines, and send geysers roaring skyward. Keep these 5 ideas in mind, and you can tackle any problem, from designing an efficient refrigerator coil to predicting the next Old Faithful eruption window with confidence. At this point, you should be able to generate a full and appropriate response to today's essential question. How does thermal energy transfer, heat, cause substances to change state?